All right. So this lecture is going to be a combination of a couple things, where we're going to look at visualizations of electric fields, the dipole, and a useful approximation technique. So, quick recap. The idea of the electric field is that a charge Q can create an electric field, and it's given by this formula, where R is the vector that points to the point of interest from the charge Q, so that the magnitude of R represents the distance between the point of interest and the charge Q. So again, conceptually, right, K, Q, and then this is the distance between the charge and the point of interest. You square it, and then this R hat is then the vector direction. That if Q is positive, then E points in the same direction as R. And if Q is negative, then it is antiparallel to R. And then we can connect these back to forces, that if there is a charge, a second charge located at some point, I can ask myself, what is the force on that second charge, capital Q, from little q? And that is given by capital Q times the electric field of little q at that point, at wherever capital Q is. So we're trying something. So I've given you essentially some of my notes more or less completed. Some of the derivations and the math work I erased, and you can see me actually work it out. But it's more or less here with the hope that, with the idea that you can just then listen and take notes on what I'm saying rather than being scribes. This is admittedly exactly what I do for Intro Astro, so it was not too galling a request. If you thought maybe asking for my own notes might be a reach. But again, it's what you get out of it. So if I'm giving you these and you're not really spending the time to think about what it is that I'm saying or have written down, because you don't have to write it down yourself, then that kind of defeats the purpose. And I'm also not claiming that I've written it down perfectly. Usually these are, I do like a few I do like maybe 2 or 3 drafts of the notes, and then I press record. Else I would do 10,000, iterations, and nothing would ever get done. So you might have a different way of writing things down or describing things. By all means, you should make those notes. But a quick thing to point out is that before, when we were talking about the Coulomb force, we often had absolute values around the charges. And when you're talking about the magnitude, of course, a magnitude is always positive, so it makes sense that there might be absolute values there. But if we're just thinking of the vector E or the vector F, you can do away with the absolute values, and the way we have defined and set out the formula, if those charges are negative, those negative signs will flip the vector appropriately. So let's just work this out for the electric field first and convince ourselves that this is true. So the top case has, I placed my origin here, my axis there, and there's going to be a positive charge Q that's located here, and then this point here is going to be the point of interest. So then I can define my position vectors based on my axes and my origin. And then the vector that goes from Q to this point of interest then is what we've been calling R. So in that case then, R hat then of course points in the same direction as R. And then again, if I think of the formula for E, where the electric field that results from Q is K, Q over this distance squared times R hat, where this thing in brackets is just a number, K is just a number and it's positive, Q in this case is positive, as we're saying plus Q, And for this lecture, red is going to be the convention for positive, blue for negative. And then the denominator is, one, it's a magnitude, so that's positive, and you're squaring it, so it's doubly positive. So in that case, everything in the bracket is a positive number. So since this entire thing is positive, then that means that the electric field as a result from Q is parallel to R. And that's because, again, if that's not clear where that's coming from, E sub Q is some positive number times R hat. So then, in this case, I'll stick with red since the charge is colored red, the electric field at that point might look something like this. Then, if the charge is negative, then you can see that nothing really changes, but the electric field better flip signs. So we still got KQ over the distance squared times R hat. And now we have K is positive, the denominator is positive, but Q is negative. So overall, that thing in brackets is negative, which implies that the electric field as a result from Q is anti-parallel to R. And that's my kind of anti-parallel symbol. So in this case, R hat still points in this direction, but then the electric field at that point is going to maybe look something, like this. And again, note that it has the convention that it goes away from positives and towards negatives. All right. So that's the electric field. So that seems like if we don't have the absolute value around the charge Q, the sign of Q takes care of itself, or it takes care of getting the vector direction correct. What now about the force? Now let's suppose same setup, but I'm going to actually put a charge at this location here, capital Q, capital Q, which will either be positive or it will be negative. And here we're going to see, again, we can work out, there's only 4 cases in this case, where capital Q is either positive or negative, and then the electric field, that Q, is either positive or negative. And we can work out the direction that this formula suggests and see if it kind of matches conceptually what we think it should be. So again, in this case, then the force takes this form, it just becomes the Coulomb force. Here we can define R as pointing not to the point of interest, but in a sense the point of interest, but the point of interest is the location where this capital Q is. Because I'm asking what is the force on capital Q from little q. So, in the case that they are both positive, we said above that the electric field points away like that. And so then I have the force is that same vector E multiplied by a positive number. So in that case then the force, since I'm just multiplying by a positive number, the force then is going to also point in that direction. Force on capital Q from little q. And does that make sense? They're two positive charges. They should repel one another. The force should have the capital Q try to move away. Okay, that works. Let me go across now. So now we have the case where capital Q is negative. So in this case, the electric field from little q, again, still points away from little q. That's the signal that little q has sent out. And capital Q hears that signal and interprets it that since it is a negative charge, it should go in the opposite direction of the electric field. And so therefore it feels a force that points anti-parallel to E. So then if we want to state this, here it seems like we said that F of is parallel to E sub Q. And here it looks like we're saying that the force is anti-parallel to the electric field. And then very quickly, the other configuration. Here the electric field is pointing in towards the charge. And so in the first case, where capital Q is positive, it's going to then just be in the same direction as the electric field. So then the force is going to look something like that. It's just going to be a positive number times the electric field. So it looks like then, again, the force is parallel to E. And then similarly, the force in this case is going to be anti-parallel. So it seems like, maybe I'll even give it a highlight. Seems like, these conventions seem to hold. When capital Q is positive, then the force points in the direction of the electric field. When capital Q is negative, it points in the opposite direction of the electric field. And then the electric field itself has the convention where it points away from a positive charge and towards a negative charge. You just got to make sure you don't confuse again, the agent and the system. The agent, little q, creates the electric field such that the electric field points away from it if it's positive or towards it if it's negative. And then capital Q, immersed in that electric field, feels a force as a result that is either parallel to E if capital Q is positive or anti-parallel if it is negative. All right. And then again, another recap from last time is that since forces obey the superposition principle, so does the electric field. So we can talk about the net electric field, which just then is the sum, the vector sum of all the electric fields, that are in the area. And again, the electric field itself is a vector, just like how forces are a vector. And when we say that forces obey the superposition principle, what that means is that F net, the vector, is the sum of vectors if there are multiple forces. And so since the electric field is a vector, the superposition principle says that the net electric field vector is the sum of the electric field vectors. This is not the same thing as summing the magnitudes. That could be very risky because there are systems or configurations where that does not make sense and clearly gives you the wrong answer. It's always nice if you can come up with simple examples, counterexamples, because then you can hold those in the back of your mind and recall them if you ever, on an exam or something. It's like, oh, can I just add the magnitudes? Is that allowed? And here's two examples of why you shouldn't just add magnitudes unless you're very careful and convinced that, that's allowed, which probably means that the vectors are all parallel to one another. So again, suppose I have two charges. I have a positive charge here, Q sub 1, and a negative charge here, Q sub 2. Nope, it looks like I assume they're both positive, even though I'll use the color scheme. That's unfortunate. Let me change. Make it blue. And the arrow tip is still, whoops. Okay, anyway. Oh, and then I gotta change this too. Silly me. Okay. So in this case, if I have a charge Q1 and Q2, and I have some point of interest that is, in this case, kind of nice and conveniently along kind of horizontal and vertical axes. Then Q sub 1 creates an electric field that points downward. That's a vector. So then I would expect the electric field E1 to maybe be something like, it might be something like red. E1 might be 0, comma, negative the magnitude or something. This is going to point downward in that case, and there's no horizontal component. Similarly, the electric field from Q2 is going to be a vector that points to the left. So then the net electric field then is the vector sum, right? So I can just add the two vectors, and then that gives me E net, which, again, adding magnitudes you would not get because those aren't vectors. But here, clearly, the net electric field is a 2D vector, even though the two fields that you added together were essentially 1D. And then another one that a student came up with in office hours is you could think about, if you push on a box with two forces that are equal in opposite direction, they will cancel each other out. So obviously in that case, the net force is 0, which obviously is not the same as if you added the two positive magnitudes together. So similarly, if I have a charge Q1 and Q2, and they're equal charges, and then I'm looking at this point that is in the middle, then the Q1 creates an electric field that points to the right, Q2 creates one that points to the left, and they should then, by the symmetry, add up to the vector sum of 0, which again is not the same as adding just the magnitudes. For these kind of yellow Y's, I've peppered them kind of throughout, as in, you might think of how you might explain that, right? Could you explain that conceptually, or could you explain that mathematically, for example? Might be kind of good, kind of little spot checks for yourself, since I'm giving you notes. All right, so what we want to do today is go to even more interesting configurations, right? Given multiple charges, the net electric field can take on more interesting configurations. If I have 3 charges or 4 charges or a continuum of charge, in a sense, infinite charges, then I need ways to visualize the electric field. I need ways that allow me to draw the electric field in such a way that I can have essentially any charge configuration I want. So one way of doing it we have seen and have been working with already, right? The fact that the electric field is a field. Where a particle is something that is defined at a single location, a field is something that is defined everywhere. So the field, and it's a vector quantity, so there are vectors. The electric field is a set of vectors at each point in space. So we could think about drawing the electric field as a vector field, where at each point you draw a vector that is parallel, or you might say tangent, to the net electric field at that location, and that indicates direction. And then you can make those arrows longer or shorter if you want to convey magnitude that way, or what often is done is a color bar is used to convey magnitude so that the arrows aren't too busy. So, but here's kind of examples of both, right? So the two examples on the left we've seen before for point charges. In this case, the arrows are being drawn such that the length of the arrows are proportional to the magnitude. So these 4 are closest, those points are closest to the charge, compared to then these points are a little bit farther away, and then these points are even farther away. And then similarly for the negative. What you might do instead is, if you had some vector field that looked like this, rather than drawing arrows of different lengths, note that I've made every single arrow the same exact length, but then I've color-coded it. And there usually then will be some sort of color map or color bar, where here I'm stating that perhaps these kind of bright yellows correspond to an electric field magnitude of 1 Newton per Coulomb. So again, I wanted to iterate that this is magnitudes of E. And then what I'm saying is that as I go from kind of this color to this color to this color, I'm going up in magnitude, up, and maybe the purples correspond to 12 Newton per Coulomb. So the color bar then tells you the magnitude, and the arrows are kind of nice and conveniently drawn. Again, such that, at this point here, for example, if there were multiple charges creating electric fields, I could then figure out the net electric field, and that is the direction of the arrow at that point. So again, each of these is kind of E net at that location. Okay, so that's the vector field line. And that's probably the way that's easiest for you to, if you were going to draw this on your own. And the next lab, I think, actually is working with a simulation software that does this for you. The other way, which has its own kind of plus, pros and cons, but it's hard to do like drawing. It's hard to draw these correctly manually. So usually you have a computer do these. That's what's called electric field lines. So in the case of vectors, notice there's a bunch of discontinuous little arrows. They're all disconnected from one another. And again, conceptually that makes sense because this electric field is specifying the direction of the electric field, but it's not saying anything about, if I were to drop a charge in that electric field, it wouldn't necessarily flow always. The path that the charge would take is not necessarily going to be always tangent to the electric field. But drawing these kind of continuous streamlines can be helpful as well as a different way of visualizing the electric field. So in this case, instead of drawing a bunch of disconnected vectors, you make some convention choices and you draw a set of continuous lines or streamlines that, again, at each point in space, the streamlines are tangent to the electric field. And in this case, then, it's kind of counting field lines where that gives you a sense of the magnitude. So, on the left, notice I just have a bunch of vectors. What you would do is, you can imagine like picking a point. Like I might pick the point, immediately above the charge, and that's going to be my starting point. And it's a positive charge, so I know that the electric field is going to move away from this charge. And then I note at that point that the electric field points straight up. So then I might take, a little step, some kind of grid cell step, and then I draw kind of a line there. And after I take this step, I then look at what direction the electric field points in at this new location. Still points up, so I take another step up. And then essentially you're just taking kind of individual steps over grid cells. And then you're drawing a continuous line without lifting your pen, that connects them all. And that's one field line. Then again, I could start here just to the right of the charge. Then I follow the electric field vector always points to the right. To the left, it always points to the left. In this case, the electric field is pretty simple. Down. And then I could also maybe go at like 45 degrees, and I would go do something like that. I would take a bunch of steps, and each time the electric field would be pointing kind of in the same direction. And I could do something like that. And then I might stop at 8. Why 8? No real reason, just because I got sick of drawing these. So essentially, what I'm saying is that if that was, say, a single proton, I'm making the convention that for a proton charge, or a proton charge is worth, or an electron charge worth, I draw 8 lines. So then notice in this case, I again drew 8 lines corresponding to negative q. And again, here, I could pick arbitrary points, in space and essentially just follow the electric field, at that point. And I could draw something similar. Then if I had something like a 2q charge, I wanted to know about the electric field, then since I used 8 lines for q for 2Q, I would use 16 lines. So then that's the convention just I chose for these drawings, right? You could choose a different number if you wanted, as long as you're consistent. But then the nice thing here is that the kind of density of field lines, right? So that there's all these lines near the center, which we know is also where the electric field is strongest. So essentially the kind of, if I draw like an arbitrary square, the number of field lines in that square corresponds in some way to the magnitude, versus if I pick over here, fewer field lines are going through that square, and the magnitude, of course, is smaller out here as you get farther away from the charge. So the density of the field lines is proportional to the magnitude. So where you see a lot of field lines crammed together, the electric field is strong. Where you don't see a lot of field lines crammed together or see them spreading out, that's where the magnitude decreases. And then you can think about, by these conventions, essentially, that's the conventions we need. Your book also lists that that field lines also can never cross. Notice that none of these you can't have something like, a field line that does this, and then a field line that does this, because something goes wrong at that point. You might think about why. Okay. The nice thing about this then, again, is that when we have something that is a little bit more complicated, we can estimate, if again, and this is why it's hard to do by hand, right? If I wanted to say I have these 3 charges here, and I had ChatGPT create a vector field, for those 3 charges. Those vectors, of course, give me a sense of the direction of the electric field at every point. And I didn't put a color map, but I could have a color map that corresponds to magnitudes. If I wanted to do streamlines, again, the thing you have to be careful is that you just have to be consistent. So I did ask that all 3 of these things were the same positive charge. So again, I could use the convention of maybe I'll use 4 lines per charge. So again, the idea of what you would do is, right, maybe I'll choose, in the 4 directions I'll go is kind of, the 45 angles, from vertical and horizontal. So then, and you can see how this would be very easy to do on a computer, or once you take computational physics next fall, you'll see why it'd be very easy to do on a computer. Essentially, I could start here at this charge on the right. I'm erasing everything. Oh my god. And then essentially I could take a step to the upper right. And then at that point, I could then follow the arrow that tells me the direction the electric field points there. So I might do that. And here the electric field kind of looks like that. Electric field is kind of like that. Electric field is kind of like that. Okay. And then these are all positive charges. So then that's one streamline. Then for the kind of lower right, it seems like then I do this, then this, then this, then this. Okay. There's another streamline. Then for the upper right, that, ooh, and then we kind of go that. Then it looks like something like that. Then to the lower, let's see, that, then we sort of swerve. So then I have my 4 streamlines for that charge. And then I can do the same thing for the other charges. This kind of just goes off, these go off. This kind of goes this way, and then it seems like it gets kind of looped that. And now I'm going fast, but I think you get the idea. So then that's some streamlines there. And this one looks like, far from the other charges, that they're just radial. But then when you get into this kind of complicated region, seems like you do something like that. So then we're getting a sense of kind of some streamlines. That again, at every location, right, at this location here, the tangent, of the streamline points in the same direction as the electric field. Essentially, it's just you're following all the little arrows. And again, I state that, to be careful that field lines are not always equivalent to the trajectory. If I were to release a test particle or a test charge, it need not follow, this path, like a streamline. That's what I almost kind of regret saying streamline, because then, like if you think like water flowing through a pipe, those streamlines are the path, the water is taking. Here, nothing's actually flowing, right? For the electric field, but it's telling you the direction, and then the concentration of field lines tells you the magnitude. If you want, again, maybe I'll just give this one to you, or if you want to think about why, right? Imagine you have a particle that is moving to the right, a charged particle that's moving to the right within an electric field that always points straight down. In that case, the charged particle is going to have some trajectory that kind of looks like that, which notice is not straight down. Okay. Now, what's really going on, and again, why this is challenging, and this kind of parenthetical here. Actually, I should put a red highlight, which means the red highlights are optional, or just asides, notes to myself. Now, really, what you have to do is you have to ensure that the number of field lines, kind of per unit area here. So essentially, you could, for any arbitrary kind of area you pluck out, they have to obey something that's called Gauss's law, which we will learn about in the next chapter. So I just say that as an aside. So again, kind of rather it'd be nicer just to have a computer do this. So I wrote some Python code to draw these streamlines for an arbitrary chart, set of charges. I drew it from kind of this American Journal of Physics paper on drawing streamlines or field lines, and some Python code from this professor, Dr. Tom Duck in Nova Scotia. So thank you, Tom. But then you can do, streamlines of kind of any set of charges that you have. So again, I'm going to stick with the convention that red is going to be a positive charge and blue is a negative charge. And so this first one here is what I might call the symmetric dipole. So I have a positive charge here and a negative charge here, and they both are the same charge Q, right? Maybe it's plus E and minus E, maybe it's plus a Coulomb and minus a Coulomb, whatever it is, they're the same charge. And so then by the symmetry of the situation, the field lines end up kind of having this symmetric shape that's symmetric kind of down the middle, where, again, they leave from the positive and then go towards the negative. But then notice kind of in between them, right, you're kind of very close to the positive and the negative already, so notice they're kind of bunched together. I expect the electric field to be strong in this region. And then it kind of gets spread out when it's far away from both of the charges and kind of loops around, above and below. Because again, you might wonder, like, okay, where does loop come from? Let's see, right and white. Well, imagine that this were my point of interest. Oh my gosh. Imagine this were my point of interest. Then from the red charge, right, I would expect that the electric field from the red charge is going to point away. So it's going to be something like that. So that's the electric field from the positive charge. And then the electric field from the negative charge is going to point towards the negative charge. So it's going to point something like that. And you do it carefully enough, by the symmetry of the situation, the vertical components of those two arrows cancel, and you're left with a purely horizontal vector at that point. And then you can do it for other locations as well. I also kind of like this. I'm going to erase this stuff, though. In that we know conceptually that opposite charges attract, And this kind of gives me a visualization of what attraction might look like with these kind of streamlines. Because the fact that they're kind of connected here, like they're kind of glued together in a sense. There's something that's binding them, and I could imagine them being kind of drawn to one another. Versus when I have two identical charges, two positive charges, then I can draw the streamlines, or the field lines rather, and kind of in the middle, right? Notice how it's kind of like the field lines are kind of like, diverting themselves from each other, right? They're not going to the other charge because so it kind of feels like they're like making a wall that is kind of pushing the two apart, which is kind of cool. And then you can be creative and do other cool things. So this would be kind of what's called a bias dipole, right? So that I think I used 2q of a positive charge and then just negative q for a negative charge. So there's more positive. Notice then there's more streamlines. There's twice as many streamlines coming out of the red as is going into the blue, because there's twice as much charge. And then as a result, right, the electric field is stronger because right there has that kq in the denominator or in the numerator. So then when you figure out the net electric field vector, you get something that's a little bit lopsided. Then you might sound like a linear quadrupole. So again, there's a 2q charge and negative charge in the center, and then just a plus q and a plus q. So there's in a sense kind of four charges. There's what's called a linear quadrupole because they're all in a line, and two of the charges are essentially on top of one another in the middle. And then again, you get the kind of attraction going on, so the field line's kind of connecting, and it's kind of this clover thing going on. And again, the direction is such that it goes out from positive and towards negative, or out from positive, or out from positive. Then a kind of traditional 2D quadrupole, right, is plus q, negative q, negative q. It gets this kind of like flower thing. Kind of looks cool. Then if you want to go towards things like continuum, right, I might ask what's going on for like a single plate. And for the plate, you can imagine that it's just a bunch of q essentially stacked very, very close to one another. I kind of drew that over here, where you can think of the continuum as just a bunch of charges very, very close to one another. So you can imagine for each one of these, I compute the electric field and then I add up. And the net electric field is then the kind of vector sum of these 10,000 individual charges. Again, easy to do on a computer. And it looks something like this. And again, note the symmetry of the situation, right? The kind of vertical symmetry makes sense that it has to point kind of away because it's pointing away from positive. And there's no reason why it should be horizontal along this line of symmetry because the charges are entirely kind of within this plane. And then kind of this line of symmetry, notice that essentially the top is a mirror image of the bottom, which makes sense. So then you can get to something more interesting like parallel plates, something we will come to love in this class when we get to circuits and capacitors. So in this case, I have a positive plate and then a negative plate. And notice that outside of the plates, I get kind of my usual kind of towards negative, away from positive. But interestingly, in between the plates, we will see that one, the electric field is essentially horizontal, right? So it just goes directly from the positive to the negative plate. But you do get these kind of fringe effects kind of near the edge. Essentially, within the plates, it's purely horizontal. And it also turns out that it's uniform, right? Notice that the kind of spacing between the field lines is more or less the same everywhere, which suggests that the magnitude is the same everywhere. So we will come back to this and see this again. The parallel plate is something we'll use a lot. But this kind of introduces the idea here. So, kind of fun to draw these things for these electric field lines. All right, so that's going to end part A in case my connection breaks and I don't want to start everything over again. So see you for lecture B.